Hello, in this video I'm going to be discussing the behavior of RC circuits with DC sources. So an RC circuit stands for a circuit with a resistor and capacitor in series. And what that looks like is you have a voltage source. Again, in this case we're working with a DC voltage source. We'll call that Vs. So this has voltage Vs. And then this is connected in series to a resistor and a capacitor. So this resistor, let me redraw this. The resistor, we'll call that a resistor with resistance R. And this capacitor will have capacitance C. So this is a basic RC circuit. And we can examine the properties of this RC circuit and how it behaves over time with calculus. And now this is an RC circuit that's charging, or that's going to be charged if we assume that the capacitor starts out with 0 volts. If we want to examine an RC circuit that's discharging, this voltage source would be replaced with a short, and the capacitor would start off charged. But we'll get to that later. So first, I'm going to review properties of capacitors. And so capacitors, they're basically, at its most simple form, just two conductors that, two conducting plates that are a close distance together so that they can store charge. And the capacitors are governed by the equation Q equals CV, which means that if you plot the charge across, like the charge on one of the plates, or like the net charge, so yeah, if you plot the net charge on each plate and the voltage across the plates, you'll get the straight line where the slope is the capacitance. And then, so things about capacitors are that capacitors, they can be thought of as resisting, they resist instantaneous voltage changes. So they resist voltage changes because, like this graph, the voltage can't change without the charge changing, and for the charge to change, there has to be current through the capacitor. So the faster the voltage in a capacitor changes, the more current has to flow through it. So capacitors in that way can resist instantaneous voltage changes. And we'll see that later as we examine the charging and discharging of an RC circuit. And then another thing about capacitors is that based on, again, after we'll see this when we work this out mathematically, is that capacitors will charge or discharge until the capacitor voltage matches with the circuit voltage. And what that means is that if you remove the capacitor after it's fully charged or discharged, the voltage at the terminals where the capacitor used to be will be the same as the fully charged or discharged capacitor. And so once the capacitor is fully charged or discharged, it'll match the potential of the circuit where it's placed. So again, if you remove the capacitor, the circuit at those 2 points where the capacitor was originally collected will be at the same potential as the capacitor when it's fully charged or discharged. So we'll charge and discharge or discharge until capacitor voltage, so VC, matches circuit voltage. Okay, now with these in mind, let's work out the behavior of a charging capacitor mathematically. So when it charges, so again, this is charging. So we're starting off with a fully discharged capacitor. We're assuming it starts off at 0 volts across its plates, connected to a voltage source of Vs in this resistor capacitor series configuration, which we call an RC circuit. And so for charging, first, by Kirchhoff's voltage law, KVL, we get the equation that Vs minus IR, where I is the current going in this direction through the series circuit, minus IR minus VC, which is the voltage across this capacitor, is going to be equal to 0. Alright, so because then this is just the voltage, Kirchhoff's voltage law, and voltage of the battery minus the drop of the voltage across this resistor minus the voltage across this capacitor is equal to 0. Now, we can replace VC, we can substitute that with Q over C by this relation we have up here. So VC is equal to Q over C. Another thing we can do is we can replace I, the current, with dQ over dt, because this is what this is the representation of current as charge over time as the limit, or the limit of current as charge over time as time goes to 0. So current, again, this is equal to the limit as time, or changing, like this time interval goes to 0 of Q over delta T. And so, again, this is a representation of current as a limit. And then when we do these two substitutions, then we get that Vs is equal to R dQ over dt plus Q over C. And now we just have a differential equation. And so we can rearrange this and then integrate to solve the differential equation. So what we get then is Vs minus Q over C times 1 over R is going to be equal to dQ over dt. Alright. And then rearranging this again, we get that 1 over Vs minus Q over C dQ is equal to 1 over R dt. And now we integrate this, so from Q, we start with 0 charge on the capacitor. We want to get to Q, which is the charge of a fully charged capacitor, we'll say in this case. Or really, Q is just the charge on the capacitor. When it's fully charged, well, we can see that when we work out the solution to this differential equation. And then from time, we want to start again from 0 time to the current time across, that has passed since the capacitor has been connected. So working this out, we get that this is equal to negative C ln of Vs minus Q over C evaluated from 0 to Q. And this is equal to, and these variables were being a bit bending the rules a little bit, but it works out the same. So this is equal to 1 over R. So this is equal to T over R evaluated from 0 to T, which is just T over R. So now, evaluating this left-hand side, we get that, first I'm going to move the negative C over. We get that it's ln of Vs minus Q over C minus ln of Vs, and this is equal to T over negative RC, or just negative T over RC. Using log properties, we can write this as ln of Vs minus, and then remember Q over C is just equal to Vc. So we can replace that as Vs minus Vc over Vs. And this is equal to negative T over Rc. Now we raise both sides, or we take E, we exponentiate both sides. So we raise E to the power of both sides here, and then that gives us Vs minus Vc over Vs is equal to E to the net, because we're trying to get rid of this log, is negative T over Rc. And now if we rearrange this a bit, we can get that Vs minus Vc is equal to Vs e to the negative T over Rc. And then if we solve for Vc, the capacitor voltage, we get Vc is equal to Vs minus Vs e to the negative T over Rc, which is equal to Vs times 1 minus e to the negative T over Rc. And this we can see is a simple type of exponential decay. Well, the e to the negative T over Rc, that's exponential decay. And then this reaches a limiting value of Vs. And so let's graph this out now. Again, this is for a capacitor that's charging. We get Vc here, the capacitor voltage, and then we plot that with respect to time here. So this is time, I'll just call it, time t. So it follows this equation. So we know the limiting value of this as t approaches infinity is going to be equal to just Vs, the source or the circuit voltage here. So that's the limiting value. And then the capacitor voltage will just be starting at 0, and then it will exponentially, or it'll grow like an exponential decay function that's been reflected and approach that limiting value as time goes to infinity. So this is what the capacitor voltage looks like when you're charging it starting at 0 volts. Alright, so now let's examine this graph a little bit. So when t equals Rc, so this is Rc here, this Rc value we call the Rc time constant. And the Rc time constant is just the resistance multiplied by the capacitance of the circuit. And for DC circuits, it gives you an idea of how fast or slow a capacitor charges and discharges. And so when t equals Rc, we see that this is just e raised to the negative 1 power. And that means that after Rc seconds of time, the capacitor is going to be at roughly 0.632 of Vs, or 63.2% of Vs. And that comes from the fact that 1 minus e to the negative 1 is about 0.632. And from this, we can also see that the limit of this function is Vs as t approaches infinity, but that means that the capacitor voltage ideally will never actually reach the source voltage. It only get closer and closer. But in real life, after a few, like 4 or 5 time constants, it gets to about like close to 99% or past 99% of Vs, and that's close enough to call the capacitor fully charged. Now one more graph we'll look at is the current graph. So if we look at the current for this circuit, we get that current, while the current is equal to the current across the resistor, since it is a series circuit, and the resistor current is just equal to V minus VC over Vs. And we can see from here, V minus Vc over Vs is just equal to V minus, so, or, yeah, this is the current, V minus Vc over R, sorry, V minus Vc over R. And V minus Vc over R is just equal to, Vs minus Vc here. Vs minus Vc over R. Vs minus Vc here, we see is just equal to Vs times e to the negative t over Rc, and then this over R. Now Vs over R is going to be the current that is, well, that's going to be the initial current of the circuit. So it's the initial charging current of the capacitor. And it's also going to be equal to the current if the capacitor was replaced with a short. So just the battery and this resistor will give a current of Vs over R. And so we'll call this current I0 or I0. So I0 is equal to Vs over R. So Vs over R. And so we can rewrite this current equation as the current through the circuit is equal to I0 times e to the negative t over Rc. Okay, so now if we graph this, we can see that graphing current over time, we get that this current starts at this I0 value, and then it will slowly exponentially decay to 0 as time approaches infinity. Again, the limit is going to be 0 as t approaches infinity, but it never actually reaches there. It just gets really close. And again, if we look at this Rc time constant, after Rc seconds, this current will reach a value of about 0.368 I0. So that's after one Rc time constant has passed, it will reach 0.368 of its initial I0 current. Sorry, I forgot to put the subscript there. So this will be I0. Alright, so when you're charging a capacitor, the current exponentially decays and the voltage gets close by this exponential decay graph to the limiting value of Vs. Okay, now let's look at the behavior of a discharging capacitor. So when a capacitor discharge in a discharging RC circuit, we have just a resistor that's in series with a capacitor, and the capacitor will discharge through this resistor when the current will flow like that. So I. Now through KVL, again we'll start with KVL, Kirchhoff's voltage law. We get that the voltage across the capacitor is going to be equal to this current times resistance is equal to IR. And now again we have the voltage across the capacitor is equal to Q over C. But this time we have the current here is equal to negative dq over dt. Now why is this negative this time instead of positive? Well, before we were charging the capacitor, so this charge on the capacitor was increasing with time, but this time we're discharging the capacitor, so as current flows, the charge on the capacitor is going to be decreasing with time, so we have to do negative. We have to put a negative in there. So this gives us that Q, all right, lowercase q, Q over C is going to be equal to R times negative dq dt. So we're multiplying here. And now if we rearrange this a bit, we get that dq dt is equal to negative q over rc. And then rearranging this again to integrate and solve, we get that 1 over q dq is going to be equal to negative 1 over equal to 1 over q dq is equal to 1 over negative 1 over rc dt. And again, we're integrating from 0 time to the current time, and then we're integrating this from fully charged, we'll just call that q, to the current charge, or q0 we'll call fully charged, or the initial charge, to q here. So q would be current charge. Okay, now evaluating these integrals, we get that this is equal to ln of q. So we're ln of q evaluated from q naught to q, current charge, is equal to t over rc, negative t over rc from 0 to t, which is just the same as negative t over rc. And this left-hand side is equal to ln of q minus ln of q naught, which is equal to ln of q over q naught. And again, this is equal to negative t over rc. Exponentiating both sides, we get that q over q naught is equal to e to the negative t over rc. And rearranging this, we can get that q is equal to q naught e to the negative t over rc. Now this gives the charge on a capacitor as a function of time, but if we want to find the voltage as a function of time, then we just need to apply this equation, which is voltage is equal to q over c. And since c is a constant, if we just divide both sides by c, then we get that the voltage across the capacitor is equal to V naught, which is the initial voltage of the capacitor, times e to the negative t over rc. So again, graphing this one, graphing this equation, we see that this equation will just yield a graph of, if we graph V, Vc, the capacitor voltage over time, we get that we start at a value of, this is just V naught, the initial charge of the capacitor, and then we get an exponential decay towards 0 as time approaches infinity. And then same thing with RC time constants is that after one time constant worth of time, this will reach around 0.368 V naught. And then if we look at the current again, we get that this current is just going to be equal to the capacitor voltage divided by this resistance. And since resistance is a constant value, this graph will look the same, which is that the graph of current over time for a discharging capacitor will look like, well, it starts off at some initial current. So let me write this. So if we divide both sides of this by R now, like that, we'll just get that the current is equal to the initial current through this capacitor, or through the circuit, and then times e to the negative t over rc. So we start off at this initial current, and then it decays towards 0, and then again at one RC time constant's worth of time, the current flowing will be around 0.368 of the initial current. One more thing is that this RC time constant will work out to have units of seconds, and then it can be represented by the Greek letter tau. So tau is equal to RC, and then this will have units of seconds. All right, thank you very much. And I hope this has been helpful in examining the behavior of RC circuits with DC voltages and sources.